Integration is one of the most fundamental concepts in mathematics. In the real sense, we study it in high school calculus as the area under a curve. In probability theory, we treat it as a mean or expected value. While the geometric interpretation and results of real-valued integrals are fairly easy to understand, at least when it comes to the standard Riemann integral, the complex counterpart is less intuitive. Here, we discuss Cauchy's integral theorem, one of the most fundamental concepts of complex analysis, and a powerful tool that helps us better understand our more familiar real number domain. Let's begin by looking at a standard degree 4 polynomial in the real Cartesian plane. The function in blue is a function in one variable, x, and shows how the value of y changes as x changes. There is one and only one way to get from a point A to a point B going along this blue path. Because of this, when we talk about the integral from a to b, or in this case, from x equals 1 to x equals 4, we have a really clearly defined notion of the area under the curve, and the definition we talk about is pretty unambiguous. Now let's hop into the complex plane. Let's take a look at the holomorphic function mapping the complex number z to another complex number z squared. The moving blue lines show how each point in the complex grid maps to a different point under this transform. The important thing to note here is that there is no well-defined path between two complex numbers. Because of this, we need more information to compute the integral than just the start and end points we can use for regular real Riemann integration. The value of the contour integral depends on which contour we choose. In other words, how we decide to travel from a start point to an end point. The particular result we're interested in was first determined by Cauchy in the early 19th century as a means to evaluate some pretty complicated improper real integrals. This result, when further developed into the Cauchy integral formula and the residue theorem, allows us to determine the solutions to otherwise intractable real integrals. While I won't fully develop all of these ideas here, this should give you a good indication of how fundamental this theorem is and the vital place it holds in the broader realm of complex analysis. We need a few more specifications before we get to the theorem, proof, and examples. First, we need to specify exactly what kind of contour we're interested in. A contour is nothing more than a directed path on the complex plane along which we may take the integral. Let's take a simple contour. This yellow S shape is an open contour, or simply just a smooth curve. It is continuous and has a start point that is distinct from its endpoint. This figure 8 shape is a closed contour, meaning that the start and end points coincide. However, we call this non-simple because the curve intersects itself, in this case at the origin. Cauchy's result relies on a third type of contour, the simple closed contour. This type of curve starts and ends at the same place and never crosses itself, and is very nice for us to work with. But where exactly does this contour live? We're pretty reliant on this curve, so we should also pay attention to the set this curve lives in. A set is path connected if every pair of points in the set has a path connecting them that is also contained in the set. The green set here is not connected. The blue set omega here is path connected, but there's another property that we need. A set is null homotopic if every simple closed curve in the set can be shrunk continuously down to a point, entirely within the set. This set is clearly not null homotopic. A set which is both null homotopic and path connected is called simply connected, and it is these sets that we define Cauchy's theorem on. Cauchy's theorem states that if omega is a simply connected open set, if f is a holomorphic function on omega, and if gamma is a closed, simple contour whose interior is also in omega, then the contour integral of f over gamma with respect to z evaluates to 0. To prove that this is true, we need to recall two important formulas. Green's theorem from multivariable calculus gives us a way to transform a line integral into a double integral over the region bounded by that line. Secondly, since f is holomorphic, it must satisfy the Cauchy-Riemann equations, as shown here. We can now proceed with our proof. First, we rewrite the integral, since f can be expressed as u plus iv, and z can be expressed as x plus iy. Using linearity, we can then split the integral into two, factoring out the imaginary I in the second. We then apply Green's theorem, converting both contour integrals into double integrals over a region. Substituting using the Cauchy-Riemann equations immediately shows that both integrands are zero, meaning the overall integral does in fact evaluate to zero. Let's consider an example. Consider the function 1 over z, and let our contour be the unit circle. Using the substitution z equals e to the it, we can rewrite this contour integral in terms of a real integral with respect to t. Simplifying the integrand and evaluating shows us that this integral evaluates to 2 pi I. This seems to be in violation of Cauchy's theorem. However, recall that one of the requirements of Cauchy's theorem is that the function is holomorphic everywhere on the open set omega, meaning that it must be holomorphic in the region bounded by the contour. Since 1 over z isn't even defined as z equals 0 within the contour, Cauchy's theorem does not apply, explaining our result. Now let's cover a true example. Consider the function z squared, and once again, let our contour be the unit circle. Now we have a holomorphic function integrated over a simple closed curve in a simply connected domain, so Cauchy's theorem should hold. The final result should be 0. Performing a similar set of substitutions as before, and evaluating the final integral at 2 pi and 0, we end up with the result of 0, just as we expected. To finish off, let's extend this concept further to a critical application. From this property, we are able to derive the Cauchy integral formula, which allows us to draw a strong conclusion between complex differentiation and integration, and allows us to evaluate complex integrals extremely easily. Suppose we have a function f which is entire. In that case, we can take a circle C and a point inside the circle z0. Let g be the function defined as shown, f of z minus f of z0 over z minus z0. Clearly, g is discontinuous and therefore is not analytic as z0. However, since by definition, the limit as z approaches z0 of g is exactly the derivative of f, we can then use continuity and let g of z0 equal f prime of z0. Now we will show that the contour integral of g about the circle C equals 0. The integral of g about the circle C sub r should equal the integral about the circle C, which is a natural consequence of Cauchy's theorem. Since g is continuous and therefore bounded, we can take the limit as r goes to 0 and see that the integral on C sub r must be 0. So the integral of g on C must be 0 as well. Then simply rearranging terms and using the result from our bad example earlier of 1 over z yields the final result for Cauchy's integral formula. Cauchy's integral theorem is of great significance for a variety of reasons. Not only does it greatly simplify a good deal of the confusion surrounding the complex contour integral, but it naturally leads into proofs such as the one just shown, the ideas for the residue theorem, and can even be used to prove the existence of power series representations for holomorphic functions. Cauchy's theorem is a tool that is integral to the foundations of complex analysis, and its applications are both fascinating and profound.